It's my honor to introduce Dr. Erez Karpas. He is a senior lecturer at the Faculty of Industrial Engineering and Management at the Technion Israel Institute of Technology. His main research interests are artificial intelligence and robotics. And prior to that, he was a postdoctoral associate at the Model-Based Embedded and Robotic Systems Group at MIT, under the supervision of Professor Brian Williams. Before that, he was a research fellow and the research coordinator of the Technion Microsoft Electronic Commerce Research Center under Professor Moshe Tenenholz. And he completed his PhD under the supervision of Professor Carmel Donschlag and Professor Shaul Markovich at the Faculty of Industrial Engineering and Management at the Technion Israel Institute of Technology. So with that, you can please take it away.
Okay, so thank you, Rafael, and all the other organizers for the invitation. I think the talk I'm going to give touches on 3 of the 4 subjects that you mentioned. So we've got multi-agent systems, we've got verification, and we've got robotics, or at least a story about robotics. Not software engineering, I'm afraid. I'm sorry. Maybe we'll get to that. And so what I want to tell you about is kind of a research project I've been working on for the past several years, which deals with social laws. So I'm going to tell you about robustness verification and about synthesis. But first, let me give you some motivation, right? So we all know that robots operate in the real world, right? And know that I'm saying robots in plural. And I think I don't have to tell anyone here that multi-agent planning is hard, okay? Even if single-agent planning is easy, and it's not, but even if you have a lot of easy planning problems for several agents, then the combination becomes hard. So what we're trying to do here is enable each agent to plan on its own without considering what the other agents are going to do. Okay, and if we're able to do that, then we'll be able to make the planning problem much easier for everyone. So just so we have some math early on, if you've never seen strips before, then I apologize. But we're going to use a formalism that's very similar to what's called multi-agent strips, except that in multi-agent strips, there's a common goal and we have an individual goal for each agent. So we can describe our setting as consisting of a set of facts. So these are binary propositions, right, that are true or false, and they characterize the state of the world. We've got an initial state, which is what are the true facts. Each agent has a goal, and these are the facts that the agent wants to make true. And each agent has a set of actions, and they have preconditions and effects. So this is the setting. So I want to give you an example. And the example is a very simple one, which is an intersection, right? So you've got cars that want to cross an intersection. So we can model it by dividing the world into these 12 different regions, right? So here, 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 etc. Right? So we can say that the facts that are used to describe the state of the world are at car region or clear region. So we have a set of these facts and they characterize who's where. And our actions are driving. So a car drives, let's say, from this region to this region. Of course, they have to be adjacent. Or a car can arrive. So we model a car appearing as this arrive action. So let's look at an example plan for the red car that wants to cross the intersection. And this is, in fact, an easy planning problem, right? So it arrives here and then drives from the west entrance to the southwest corner of the intersection, then from southwest to southeast, and then to the east exit, etc. So the single agent planning here is very easy, right? We can look at 2 plans, one for the red car, right? And one for the blue car. And the question is, can these plans interfere with each other? Okay. And obviously the answer here is no, right? Because there's no way for these cars to hit each other following these plans. But what happens if we've got the green car driving down from the north and the red car driving east from the left? So these plans can actually interfere with each other, right? So specifically if we execute them in this order, right? So first the red car arrives, then the green car arrives, then the red car drives 1 slot, and then the green car drives 2 slots, and then they crash. We don't want cars crashing, okay? That's our main motivation here. So social laws can help us here. So what's a social law? A social law is something that restricts the set of legal actions that are available to the agents. Okay, and this idea was introduced by Moshe Tenenholz and Yora Moses and Yoav Shoam over 30 years ago. So the first paper was 1989. And this is motivated by laws in the human society, right? So the same way we have laws that tell us cars drive on the right, or maybe some of you are from the UK, right? Cars drive on the left. That's fine. As long as everyone follows the law, we are guaranteed that cars are not gonna have head-on collisions, right? So what do we get from social laws, or let's say from a good social law? So there are two things that we want. The first is robustness. Robustness means that a social law guarantees that the agents can achieve their goals. So each agent can achieve its goal. And I'll have a more formal definition of this later. The other thing, which I'm a bit sad to say that we haven't done too much about, is efficiency. So we want to make sure that plans that obey the social law are as efficient or almost as efficient as plans that don't, right? Because if obeying the law is expensive, then maybe agents will have an incentive not to do that. So keep that in mind, but we're not going to talk about that today. Okay, so how can we formalize the notion of social laws? So we said that a social law restricts the set of legal actions that are available to the agents, right? So we can look at a social law as something that takes as input an MA strips planning setting and outputs another MA strips planning setting, right? Where maybe some of the actions have been removed or some actions have added preconditions or something like that. But these types of social laws will have a limited usefulness because what's missing here is some synchronization, okay? So if we take the intersection example, right? A good social law for the intersection example has to include some form of yielding, right? We know that that's the way the real, traffic laws work, right? A car needs to yield for another car coming from the right, okay? And so in our setting, we enhance the MA strips formalism by allowing us to annotate some of the preconditions as what we call wait for preconditions. Okay, so what are the semantics of wait for preconditions? Basically, we say that when we execute an action that has a wait for precondition, then when the executive is given an action with wait for preconditions to execute, it won't actually start the action. It won't actually dispatch the action until those wait for preconditions are true, okay? So this means we have two types of preconditions. Those that are marked as wait for, which means that the agent, the executive, the robot, right, will check if something is true before starting the action. And those that are not marked as wait for, which means that if the agent tries to execute an action which has a false precondition that is not marked as wait for, then it will fail, right? Something will go wrong. So why not mark all preconditions as wait for, right? That seems to make sense. So the problem is that if you look at the kind of inspiration for this, motivation for this coming from a real robotic system, then it doesn't make sense to wait for something that the robot can't sense or can't know, right? So we can't mark some precondition as wait for if we can't actually check that it's true, because then we won't be able to implement the executive. And so this wait for mechanism, I think, is interesting, and there's some interesting work to be done in understanding what it actually means, I think. Okay, so now we can more formally define the execution model, which we will use to define what robustness means. So we have the multi-agent setting that we talked about, right? So facts, actions for each agent, initial state and goal for each agent. And we can define the projection of this setting for each agent as a single agent strips planning problem, which consists of the same set of facts, because the facts are common, the same initial state, because the initial state are also common, and just the actions of agent I and just the goal of agent I. So this is a single agent planning problem, which we can use any classical planner that you like and solve. Okay, so the execution model says that each agent I has some plan pi I, which solves its projection. So that basically means that the agent has come up with a plan that assumes that the other agents are not going to do anything. Okay, and then how do we get multi-agent execution? So we have some scheduler which chooses which agent acts next, right? So you can think of it as there are, n different plans, and then scheduler says, okay, agent 1, now you execute your first action. Okay, agent 5, now you execute your first action. Okay, agent 1, now you execute your next action, et cetera, et cetera. Okay, and the only restriction on the scheduler is that it has to choose an agent whose next action has wait for preconditions that are satisfied. Okay, so it can't tell an agent to execute an action that has a false wait for precondition. This is basically the meaning or the semantics of wait for preconditions. And we don't make any other assumptions about the fairness of the scheduler. Specifically, the scheduler can be adversarial. Okay? So under this execution model, we get two possible types of errors. So the first type of error you can see on the left, I hope it's also on your left, is a collision. That basically, right, in the intersection example, that's cars crashing, and that means in our formalism that an agent executed an action whose precondition does not hold. So obviously this can't be a wait for precondition, but if an action has preconditions that are not wait for, and it tries to execute an action that has a false precondition, it will fail. So we call this a collision or a crash or whatever, failure. The other type of error you can get is actually a lot more interesting, and that's a deadlock, right? So what you see here is basically the classical example of a deadlock from a computer science textbook, right? Where if the social law means that each car yields to the car coming from the right, then what you have here is a deadlock, right? Because this guy is waiting for this guy. You can't see my pointer, right? This guy is waiting for this guy. This guy is waiting for this guy.
We can see the pointer, yes.
I see. Okay, excellent. So this guy's, etc. Right? So everyone is waiting for someone else, and no one can actually move, right? So formally, this means that all agents are waiting for some precondition, or they're already finished. So there's no agent that can act next. So these are the two types of errors that we want to make sure don't exist in our social law. Okay, so we can define two notions of robustness. I won't go into the details for both of them. I'll just focus on the main one, which we call rational robustness. And what this means is that any agent can choose any plan for its single agent projection, and the scheduler can merge them in any way that it wants that respects wait for preconditions. And then after you finish executing this trace, then every agent's goal will be achieved. Okay, so rational basically means that every agent wants to achieve its goal. We also define the notion of adversarial robustness, which basically means that one agent wants to achieve its goal and all the other agents don't care about their own goal, they just want to ruin that agent's goal. So this is a stricter requirement, but it's an easier verification problem, but I won't get into the details here. Okay, so how can we verify if a given social law is robust? So what we did here is we cast this problem as a classical planning problem, which tries to find a counterexample. Okay, so this is basically a form of directed model checking, right? So why can we do this? So our planner can choose the plan for each agent and control the scheduler. And we can do this because we assume that the scheduler is adversarial. Okay, so the goal of the planner in this setting is to choose plans and then find some way to interleave the actions in these plans which causes an error, right? And we said that there are two types of errors. So the caveat is that we also have to make sure that each plan works by itself, right? So we need to come up with a set of n plans, one for each agent, that work if they were executed by themselves, and don't work when you sequence them together in some way, okay? And if there's a solution to that planning problem, then the social law is not robust. So this means that if there's no solution, then the social law is robust. And so what we did to actually get this working in practice is we used planners from the unsatisfiability competition, which are tailored towards proving that there's no solution. And these actually work better to prove that the social law is robust. So I won't bother you with the details. They're long and excruciating, and you can find them in our ICAPS 17 paper. What I want to do with the remaining time I have is talk about some of the extensions we did, but maybe first I'll show you some examples. Okay, so these are examples of the verification procedure I showed you. So we have the intersection example I described before, and we can look at the empty social law, which means that there are no restrictions whatsoever. So if we run our verification algorithm, then we get a collision, right? Because these two cars can easily crash into each other. So then we can look at that counter example, right? And say, okay, I want to fix that. How can I fix that? Well, we can try to have a social law which says, don't drive into a location that is not clear, okay? So this seems to make sense, right? If there's a car in front of you, don't drive into it. But then we can get a deadlock, right? Because each car can drive one step and then they're all stuck. Okay, so we can say, okay, maybe this is a bad idea. Let's try a different social law. Let's try to learn from traffic and say, yield to a car coming from the right, right? As we saw before, this is also a deadlock because each of these cars is waiting for the others. So finally, we can come up with a social law that says that cars coming from the north or the south yield to cars coming on the right, okay? And we can actually prove this. This is robust using our compilation and basically any planner you want, because this is a tiny problem in terms of its state space. Okay. So what I talked about so far, right? So I connected social laws to multi-agent planning. I defined the notion of robustness. And then I showed you how to check whether a given social law is robust by compilation to classical planning. What I didn't show you is that this actually works quickly on some benchmarks from the multi-agent planning competition. All right. So now let's talk about some extensions to this work that we did. So I kind of gave you robotics as motivation for wait for preconditions, etc., but I didn't do much more than that. So we already said that robots operate in the real world, right? And another feature of operating in the real world is that actions take time. Right? So in the previous formulas, we had instantaneous actions, A1, A2, A3, A4. But if you've ever tried to get a robot to go from A to B, you know that it takes time. And we can't assume that robots execute actions turn by turn, okay? If we wanted the robots to execute actions turn by turn, we'd actually have to solve a much more complicated coordination problem than what we're doing here. So instead, what we did was we extended the idea of social laws to a formalism that has continuous time and durative actions. So if you're familiar with PDDL 2.1, that's what we used. So the idea is that each agent follows a sequential plan, right? And each action takes some time, but multiple agents can execute their actions concurrently, okay? So using this formalism can actually simplify the intersection example considerably, right? Because then you just have one action which is cross the intersection. You don't actually have to worry about the exact location of each agent in the intersection. And you just want to make sure that you don't have two actions, let's say cross from the east and cross from the north, that are happening concurrently, okay? So this is much, much more simple to model. So the reason we restricted ourselves to sequential plans is that actually what happens is that when agents have a partial order plan, so when the plan for each agent can have multiple actions for that agent executing in parallel, then we get uncontrollable durations kind of through the back door. And if you're interested in why, then we can talk about that later. The interesting thing about using this formalism is that you get a lot more types of failures or failure modes, right? Because one thing that can happen is that an action can violate the invariant condition of an executing action. So we have to check whether some action causes a failure, a collision, not just when that action starts, but also when the action ends. And we have to make sure that if the action has an invariant condition, right, something that has to hold throughout the execution of the action, then no other action violates that. And then waiting in this formalism is trickier because we can't rely on a turn-based mechanism that says an agent will wait until the scheduler calls upon it, right? So waiting here actually happens in real time. So we handle all of these, and we have a compilation to temporal planning rather than classical planning. You know, the excruciating details for this are in a paper from AAAI19. And I should say this is work by my student Ronen Nir. So you know, I'm an assistant professor now, so I get my students to do the work, and I take all the credit. But really, they deserve it. All right. So that's one extension. Another extension that was actually presented at ICA yesterday by Alex Tuisov, another student of mine, is dealing with reactive agents. Right. So so far we assume that agents plan offline, and then they commit to that plan. Right. Even if they see that the plan is going to fail, they don't change anything. And that doesn't make too much sense in you know, real settings. So what we did here is we addressed the case where agents can replan online when something goes wrong. And this actually introduces a new type of failure, which is a live lock, right? So for example, if there are two people that want to cross each other in the hallway, and then each keeps getting out of the other's way, right, they can get into this infinite loop. So you can see the details in the paper, or since you know ICA is virtual, then at least you can just watch the recorded talk. I'll just show you this example here. So there are two agents, 1 and 2. 1 wants to get here, 2 wants to go here, and these are their plans. Okay, and so let's say agent 2 goes here, then agent 1 goes here, and then he sees he can't continue with his plan, so he replans, and he goes back. And he goes back up and follows this plan, right? What this example shows, again, I don't want to go into the details of this, is note that the state of the world here, right, in this state, and the state of the world here, the state of the world here, the second state, and the state of the world here in the fourth state are the same, right? So the agents are in the same location, but their plans are different, which is why this is actually not a live lock. So you can look at the paper for the details of why this is important, but this is actually a tricky detail. Okay, finally, so far I talked about verification, right? But what if we want to actually automatically synthesize robust social laws, right? Because I mean, I can write social laws, and you know, my students can write social laws, but if you haven't, you know, had practice, and if you haven't worked with the planner to do the verification, then it's very easy to not be able to come up with something or to write something that's not robust. So you can verify that, right? But still, it takes manual work. And we want to automatically synthesize a robust social law. So what we did here was we used heuristic search, right, to search through the space of possible social laws. And we used the verification procedure that I told you about as a goal test. Okay, so all right. So first we have to define the possible modifications that a social law can make. And in the first attempt, we only said you're allowed to disallow some specific action. So the search space is still huge. So what we did was we used the counterexamples we get from our verification procedure to prune the search space. So we proved that you only need to look at the actions that appear in the counterexample. There's no need to restrict actions that don't appear in the counterexample because their social law will still not be robust. And we also had some preference to disallow actions that appear before the failure actually happened, although this is not actually always correct. And then we had a heuristic that we first tried to use the verification search effort as a heuristic, but that didn't work well. What we did do was kind of keep statistics throughout the search of which actions appear in counterexamples, and we favored those, and that seemed to work well. So we had a paper in AAAI 2020, which feels like ages ago, again by my student Renanier, and I can tell you that this works, but we're actually working on something that will be much more efficient, which I'm kind of embarrassed to say, but uses deep learning. Okay, so let me conclude and leave some time for questions. So I showed you three notions of robustness: rational, adversarial, and reactive. I showed you two formalism where we can verify robustness, which are classical and temporal. And then I showed you how to synthesize robust social laws for rational robustness in classical settings. Future work is to look at social laws with hierarchical planning, look at task in motion planning settings, look at social laws for human robot teamwork, and basically anything you can think of, right? Any formalism you want, you can look at applying social laws there. So with this, I want to thank you and shamelessly advertise ICAPS 2020, which is going to be virtual, so you can all attend from the comfort of your office or living room or whatever. And now I'll take some questions.